The second part of lesson 2.1 is where we actually get into the use. Why would we need ordered pairs? Why would we need a number that represents an x and a number that represents a y? Well, this is where we get to graphs of equations. And specifically, we're going to look at graphs of linear equations in two variables. So a linear equation in two variables is an equation like y equals x plus 2, which has two different variables. Usually they're called x and y, but they could be any other letters that you choose as well. And the fact that they're linear, when we say linear, we're meaning that there's no exponent on the x other than a 1, and no exponent on the y other than 1. Now, these can have coefficients, but the exponents have to be to the first power. So if exponents of x and y are both to the first power, then it's a linear equation. And the goal here is to actually figure out what it means to have a solution for a linear equation like y equals x plus 2. Now, just like in regular linear equations, a solution to a linear equation in two variables is something that makes this equation true. But if we have something that makes this equation true, we need a value for x and a value for y. So for instance, if we were to plug in a 3 for x, my right-hand side would be 3 plus 2, which would be 5, and my left-hand side would be y. So I had to get y equals 5. So the 0.35, if you plugged in a 3 for x and a 5 for y, it would make that equation true. Therefore, 3, 5 is one solution to this equation. Now, that is not the only solution to that equation. So for instance, if we plugged in the number 1 for x and the number 3 for y, 1, 3 would also be a solution to this linear equation in two variables. And so solutions to this equation look like points. Sometimes we call these again ordered pairs, like we mentioned in the last video. So solutions look like points or ordered pairs where we have an x value and a y value that make this equation true. Now, how many different solutions are there going to be for a single equation? The answer to that is that there are infinitely many solutions. There's infinitely many x-y combinations that you could come up with that are solutions to this linear equation. Now, I say infinitely many. That does not mean all. For instance, the ordered pair 3, 4 is not a solution. If you were to plug in the 0.34, you would get a false statement. In fact, your equation would say 4 equals 5, which obviously is false. So there are infinitely many solutions to this equation, but not every point works. So how do we represent infinitely many solutions, infinitely many ordered pairs, but not every point works? Well, we're going to do that with a line because it turns out while not every point works, all the points that do work are going to fit some pattern. Specifically, if you plug in points, if you go and check, you'll find that the point -2, -4 works in that equation. The point -1, 1 works in that equation. The point 0, 2 works for that equation. And if you start plotting all of these points that work, what you'll end up with is a straight line. So it turns out that when you are trying to find all the solutions to a linear equation, the easy way to represent those is to show the graph where every point along this line is a solution. So the shorthand version of that is just to say, hey, let's graph y equals x plus 2. But what we're really doing is we're finding a visualization of all of the ordered pairs that satisfy this equation, or in other words, all of the ordered pairs that make this equation true. Now, how do we do this in general? In general, how we go about doing this is the way I was doing this. I basically am just plugging in a number for x and then seeing what y has to be. And that's probably the easiest way, or I shouldn't say easiest, that's the first way that everybody learns to graph. We're going to graph another way in 2-2, but this method is basically a filling out a table. It's plugging in points for x and then finding points that correspond for y. So plugging in a table, I call this the table method. Other people call this plugging in values for x method. Lots of different ways to call this. Take a look at how we would do this with a problem like y equals 2x plus 5. This is the cooperative group problems. If you want to push pause and try each of these, that would be great. I'm going to, in 5 seconds, do these on my own. All right, so y equals 2x plus 5. The first thing we want to do before we actually turn to the graph is we want to create a table. We're going to create a table with an x and a y. I've created kind of a fancy one here because it's a little bit easier to do with a Word document. But we have x's and y's. And we're just going to pick some values for x to plug in. Maybe I plug in a -2 and a -1 and maybe a 0 and maybe a 1 and maybe a 2. All right, so different values for x. Now I'm going to take in each of these values and I'm going to plug in that value of x right here for the variable. So what I do is, for instance, I say, let's look at the x value of -2. So y equals 2 times -2 plus 5. Notice I plug that into parentheses just like we did before. And if you do that, what you can do is you can solve this. This is a linear equation in one variable, specifically the variable y. So now that I've plugged in a number for x, now it's a linear equation in one variable. This one's really easy to solve because all you have to do is simplify this right-hand side, and you'll see that we get y equals 1 as the answer. So what this tells me is that if you plug in a -2 for x, y is forced to be 1. So we're going to get the ordered pair -2, 1. So -2, 1 is a solution. I'm not going to write each one of these down, but I just want you to understand what I mean by that. -2, 1 is that ordered pair, and we know that it is a solution to my linear equation. And then you go ahead and do the rest of these. So now let's say we wanted to plug in the x value, the next x value, which was -1. 2 times -1 plus 5 becomes a 3. So we get the solution -1, 3. Then you plug in a 0. And again, I'm choosing 0 because it's the next x value on my list. When you plug in 0, you get a y value of 5. So the point 0, 5 is going to be on my graph. Now, the book usually has you plug in and find at least 3 points. Sometimes I go 4 points, sometimes I go 5 points. As you can see, I've chosen 5 different values for x here. That's plenty. And I usually like to go more than less because if you ever mess up on one of the calculations, then that one will kind of stick out as being goofy. So if I would have, for instance, messed up on this calculation and came up with a number other than 7, it would immediately stick out as not fitting the pattern that the others do. So there we go. -2, 1, -1, 3, 0, 5, 1, 7. And then when you plug in a 2, 2 times 2 plus 5 is 9. All right. So we can see not just is -2, 1 a solution, but also the ordered pair -1, 3, and then 0, 5, 1, 7. Again, you would just use this table as your ordered pairs. You don't have to rewrite each ordered pair. So there we go. We got 5 ordered pairs. Now that we have that, we can go and we can graph. So we have to find, again, on this paper, you would just use this graph here, and you'd plot those points, and then you'd make a line. I'm going to do that on another piece of paper, or I should say I'm going to do that on this Microsoft Paint thing. So here's what I'm going to do. Let me see if I can, yeah, let's do that. So first off, let's graph. Now the first point was -2, -2, comma, 1. So the point would be right there, -2, 1. The next point was -1, 3. So right there. The next point was 0, 5. So notice how we needed to know all of these points and how to graph things. That's because we can graph here. 1, 7 was the next point, 1 comma 7. The fifth point that we had was 2, 9. And since we've made all of our calculations correct, you can see the pattern that we get here. All right? You can see the pattern that's going on. Now, what we do when we get this is we'll start somewhere. We'll draw a line through all these points. And then usually at the very end of this line, we will draw an arrow. This is something that's not in your book, but something that's important. These arrows at the end that you will or you should see are signifying that this pattern goes on forever. So this pattern goes on forever. It goes up forever that way, goes down forever that way. So now we've graphed using the table method y equals 2x plus 5. I want you, if you haven't yet, to go ahead and try to graph y equals 3x minus 1 on your own, and then graph 2x plus y equals 2 on your own as well. Push pause, and I will do number 2 in about 5 seconds. Right, so hopefully you did that on your own. I'm going to do this fairly quickly. Um, so we're going to plug in different values for x. Again, it doesn't matter which values you choose. just so long as, you keep track and you calculate things correctly, excuse me. So for instance, I chose an x value. My first one is -3. When I plug that in, I got a y value of -10. Let me show you once how to do that again. So 3 times -3 minus 1. So plug in a -3 for x. Again, we always plug that in parentheses. 3 times -3 is -9, minus 1 is -10. So when you plug in -3 for x, the y value has to be -10. And similarly, when we plug in an x value of -2, y has to be -7. When you plug in an x value of 0, y has to be -1. When you plug in an x value of 3, y has to be 8. And when you plug in an x of 4, y becomes 11. Now, again, you could have chose other x values if you wanted. So here's the deal. Now that we have all of those points, all of those ordered pairs, now we can plot those on our rectangular coordinate system. Remember the first one was -3, so go left 3, -10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice when the numbers get bigger, you have to be a little bit careful about your count. That could throw things off. Let's make that a little bit thicker here. There we go. -2, -7 is right there. 0, -1, we go right there. 3, 8, 3, 8 is right here. And 4, 11, well, if you go to out 4 to the right, 11 is actually off our charts. And that's one of the things sometimes you do. If you pick out too high of x values, your y values get off your chart. So maybe you'd go and change that one, or maybe you'd estimate it, maybe you'd change it. I don't know. So some people change them, some people estimate them. That's what they do. But you can kind of see the pattern that we're getting here. We're going up. That is a straight line. I'm not very good at drawing straight lines, so I'm going to have Microsoft Paint do that for me. And then make sure you put arrows at the end to signify that this pattern goes on forever. We know points like 4, 11 are on there, even though they're not shown on the graph. So there you go. That's the way to graph y equals 3x minus 1. Now this last problem that I'm going to do, 2x plus y equals 2. Well, there's a number of ways you can do that, but the easiest way is to start by putting it in this pattern where we have y on one side and my other side involves x's and constants. So if we do that, it becomes a little bit easier. All right, if we put it into this y equals blank x minus 1, or in this case 3x minus 1 form. So that's what we're going to do here for 3. And then it becomes really, really easy to plug in values for x and come up with values for y. Here we go, 2x plus y equals 2. Now the easy way to do this, or I should say the quickest way to do this, is to take and subtract, let me make this a little bit, subtract 2x from both sides. If you subtract 2x from the left and then subtract 2x from the right, be careful here. This is 2x, that's the term. Getting rid of that on the left just leaves me with y on the left. When I subtract 2x on the right, 2 and minus 2x are not alike, so I cannot combine them. And that means that if I'm subtracting 2x on the left, I'm just left with a y. Subtracting 2x on the right, I'm left with either 2 minus 2x or minus 2x plus 2. However you want to write the order here is okay, but you'll see in the next section that generally speaking, we always start with the term with the x in front and then the constant term in back. That's just how it's traditionally wrote. So y equals negative 2x plus 2 is the same equation as 2x plus y equals 2. Hopefully you notice what we're doing there is one of the principal ideas that we had in the last chapter, and that is you can add or subtract terms from both sides and keep the equation true. Now it's a matter of just picking out some values for x and then figuring out what the y is. I'm going to use some traditional, I'll go negative 2, negative 1, 0, 1, 2. If I would have picked out an x equals 20, I'd have probably gotten too big of y's, but so I kind of kept right around 0. So when you do that, when you plug in an x of negative 2, it turns out y becomes 6. When you plug in an x of negative 1, negative 2 times negative 1 is a positive 2, plus 2 is 4. When you plug in 0 for x, you get 2 for y. When you plug in 1 for x, you get 0 for y. And when you plug in 2 for x, you end up with a negative 2 for your y value. So there it is, negative 2, 6, negative 1, 4, 0, 2, 1, 0, and 2, negative 2. So those are the points, or not just the points, those are 5 points on this linear equation, or that satisfy this linear equation, which will be on our line of solutions. All right, so let's go ahead and graph those just like we did before. So first point was negative 2, 6. So you go left 2 from the origin, and then up 1, 2, 3, 4, 5, 6. Make sure I count that correctly. Negative 1, 4, negative 1, and then up 1, 2, 3, 4. So there we go. 0, 2 is a point right here. 1, 0 is a point right here. And then 2, negative 2 is a point right there. So we can see the pattern here. That's pretty clear. I'm going to go ahead and make a line through all those points. And then, obviously, as always, I put a little arrow at the tip that shows me this pattern goes on forever up and forever down. So there you go. That is the idea. So that's how to graph linear equations in two variables.